to give you answers to the quiz. So I wrote AV equals lambda V. And it's funny because I remember my linear algebra course. It was one of my favorite math courses in college as an undergraduate. And the guy was a really good teacher. But in terms of eigenvalues and eigenvectors, in our book, that was not in chapter 4, it was in chapter 6. And so we worked through like chapters 1 through 4, and all of a sudden there's like 2 weeks left in the course. And he's like, oh, we got to go to chapter 6. Eigenvalues and eigenvectors. And this was our equation. I knew that A was a matrix. I knew that V was a vector. And lambda was a scalar. And if you satisfy this equation, that's what you call an eigenvalue and an eigenvector. And that's about all I knew. I guess I could solve the homework problems, so there's a little bit more that I knew that you guys will know by next week, I would say. And the only other thing I knew was that these are, quote, important. But I had no idea why. I didn't really know what they meant. And so I'm hoping that even this very first day I can give you more than this. Because this is kind of what I walked away with. And it was very interesting that much, much later, I end up going to graduate school for mathematics. And down the road, this is what I do research on. Okay? Our eigenvalue computations. And finding eigenvalues, let's say. Okay? It turns out that in this particular example, all you have to do to show that you have an eigenvalue here, and some of you did, was you take your matrix A, 5, negative 3, 4, negative 2, multiply it by V, 3, 4, and what do you get? Yeah, you actually get, if you work out the top number, right, 15 minus 12 is 3, and then the bottom number, here I have 12 minus 8 is 4, you actually get 3, 4 back. And so in this particular case, what's the eigenvalue? 1. Okay? So this is a really strange situation. We have A times V equals V. And this is what you might call a fixed vector. It's not moving, right? Back when we studied linear transformations, we showed there's a one-to-one correspondence between linear transformations and matrices. In other words, if you have a matrix, so in this case I have a 2x2 matrix called A. A is actually a map from what to what? A is a map. Yes, it's always from Rn to Rn. That's right. If it's an m by n matrix, right, m by n, I have here at the bottom.
So to a 2 by, from R1, R2 to R1.
This is from R2 to what? What's the dimensions of A in our example? This matrix is 2 by 2, right? So this is a map from R2 to what? To R2. Okay? So basically, everything on the plane gets mapped somewhere else on the plane. That make sense? If I gave you the number 1, 1, we could figure out where 1, 1 gets mapped. How? Well, we just apply this matrix, 5, negative 3, 4, negative 2, to 1, 1. And we could see where the vector 1, 1 gets mapped. Again, I like to represent vectors as arrows, right? Where does 1, 1 get mapped? It looks like it gets mapped to, well, 5 minus 3 is 2. And 4. It gets mapped to 2, 2. Okay, see that? So 1, 1 gets mapped to 2, 2. You with me? What an interesting choice I just made. Well, anyways, I can't believe it, but I think I just found another eigenvector. Because 1, 1, right? You get 2, 2, which is actually what?
2 times 1, 1.
2 times 1, 1. Right? So it shows you that that particular vector, so just like we call it a fixed vector if AV equals V, if you have AX equals lambda x, you might call that a fixed direction. Okay? So if you have any other eigenvalue besides 1, the eigenvector is a vector that ends up pointing in the same direction. Does that make sense to you guys? You know, here's a picture. I had to write a paper when I got back from my research trip last year to present to our board. And this is a picture that I found that I think explains what eigenvalues are pretty nice graphically. So again, you have 2, 1, 1, 2, right? And I like to take a look at the bottom right-hand corner of this matrix, of this block of dots, right? And if these are each units, then this is the point 10, 0, right? So I could ask, what does the map A do to 10, 0? And you can work it out, right? Where does it get sent? Well, we know how to multiply, so we get, what? 20, 10, right? And so that red dot gets mapped to, instead of at 10, it gets mapped to 20, 10. You see that? Every point in the plane gets mapped somewhere. I guess 0, 0 is a fixed point, right? It won't get mapped anywhere. But all the other points get mapped somewhere in general. And what I did was I drew a bunch of vectors, right? I have red ones, I have blue ones, and I have purple ones. But I claim that the purple ones are special. What's special about the purple ones? They're getting moved, but what's not changing?
Direction.
The direction is not changing. And something else too. The length of those purple vectors is not changing, right? Do you see that? Those are what you might call fixed vectors. Actually, if you had to give me a name for one of these vectors, what would we call that purple vector? I guess if we put it at the origin, right, then you can name it. That vector would be -1, +1, right? Looks like it. And if I take my matrix, I'm sorry, it was 2, 1, 1, 2, and I apply it, does this actually work? Let's see, I get -2 + 1 is -1, and I get -1 + 2 is, see? It's a fixed vector. You guys see that? The red vectors are not eigenvectors, right? Because why? They change direction. What about the blue vectors? Are the blue vectors eigenvectors? Yes, they are, right? What would be the identity of the blue vector? What do you think the blue vector is in this example? I think it's 1, 1, right? What happens if I take this matrix 2, 1, 1, 2 and multiply by 1, 1? I get
3, 3.
3, 3. You see that? So these blue vectors get mapped to something that's pointing in the same direction. And what's the eigenvalue corresponding to that eigenvector? 3. Okay. So I think this gives you maybe an idea of what these things are graphically. Okay? People were asking about what my answer is to problem 2. How do I say precisely why these have to be square? I like Tyler's answer. When he read the book enough and he said, well, everything it seems that has to do with eigenvalues all has to do with invertible matrices, and the only matrices that have inverses are square. I take that answer. But here was my argument. This is along the lines of what you were doing, Anthony. Suppose that A is m by n, right? Let me be really careful with this equation and think about what would have to be the dimension of V. See, if this is m by n, the only way you can multiply this column matrix by A is if its dimensions are n by 1. Right? And the only way that, but if you do multiply them together, what size matrix are you going to get? M by 1. Right? And when you multiply an m by 1 matrix by a scalar, it's still m by 1. So the only way this can work, since those are both v's, the only way this can work is if n by 1 is the same as m by 1. The only way this can work is that n has to equal m, and that means we have square matrix. So there's my argument. Okay? I thought that was along the lines of what you were saying. So, okay, so we have an initial idea of what these things are. And I think what I'm going to do, since there's only 3 of us today, is I'm going to throw you guys to work on a group discovery exercise. But I'm going to lead it off. I'm going to do the lead off here, and then I'm going to send you guys to work on this. Okay. I'm going to start us with problem 1, and then I'm going to turn you guys loose on the rest. Okay. And you are going to recognize this, I think. It says, we say a square matrix fixes a vector if A times V equals V, right? So you might say that fixed vectors are special kinds of eigenvectors, right? They're eigenvectors where the eigenvalue is 1. A, show that the 0 vector is fixed by every matrix. And guys, it says discovery, but I think if I do these first few for you, I think you can discover the rest more quickly. So I need, AV equals V is what it means to be a fixed vector. So part A just is, do you believe that A times 0 equals 0? And these are vectors, right? True? I'll say yes, we believe that. So there's my proof. B. Suppose that A fixes a vector V and that C is a scalar. Does A fix CV? What do you guys think about part B? I have to show that A times CV is the same as what?
C times AB.
Well, it's interesting. We'll do that next. We'll say that you can do this because matrix multiplication is associative. And then I like your move here where you say, I know that a scalar can kind of slide through a matrix, right? So that equals C times AV. Then what? Part B said, show that A fixes CV. So we need to show that A times CV is equal to what?
A times 3B.
Nope. A fixed vector is when A times that vector equals the vector. It doesn't move. So I need to show that A times CV, which is a vector, equals CV. Right? And it's funny because you guys did a lot of work in blue here. you guys were able to show that A times CV is equal to C times AV. And now, here's where, what's the given? Given that A fixes what? V. If we know that A fixes V, what's this equal to, you guys? V. Done. We showed that A times CV is equal to just CV. You see that? One thing that made this proof a little bit more challenging was I don't think I followed my suggested procedure of unpacking. Right? Until later. I said, we're given that A fixes V. Well, that's this piece here. We're trying to show that A fixes CV. Well, that's the piece down here. So here, I'm going to follow my procedure a little better here. Part C. It says, suppose that A fixes the vectors V and W. Does A fix V plus W? So part C says, okay, A fixes V and W. Let's unpack those statements. So how do I write that mathematically?
AV
equals V and AW equals W. And now the question they're asking me is, does, right, is it true when it says, does A fix V plus W, right? That's the question. In other words, is it true that, and Mitchell, what would I write here? When I say fixing V plus W, what does that mean?
Then we'll have to split that back out.
Yeah. A times V plus W should spit back out V plus W, right? That's what I'm questioning. Is this true? Well, let's check. Here's the given information up here, right? There and there. So if you write down this, A times V plus W, can you do anything with it? Sure. So we get AV plus AW, because we know that we can distribute. Then what?
AV equals V.
Mm-hmm.
Same for the other.
So to answer the question, does A fix V plus W? I would say yes. Okay. So this proves something here. We just proved something, although they didn't say it. So let me go through the three things we just did, right? We showed the zero vector is a fixed vector. And then we showed that if A fixes V, it'll also fix CV. And then we showed if A fixes V and W, it fixes V plus W. So there were basically three steps. What is it that we showed by showing these three things?
So subspace.
It's a subspace. Yeah. What is a subspace? The set of fixed vectors of A, whatever these are, fixed vectors of A, is a subspace of, well, I guess we'll say Rn, because A we're saying is n by n. It's a square matrix. For this whole chapter, guys, A is going to be n by n, some value of n.
Isn't that exactly what we did for number 8 on the test?
Oh yeah, that's exactly what you were asked to do, right? I guess the only difference was in number 8, I don't think I said A, I think I said T. It was linear transformation, but we understand that linear transformations are the same as matrices, really. So you're right, we did that. All right. Okay. Now there are some other parts of number 1 that I think are worth talking about. They give you an example matrix D. Do you understand what this means? Suppose that D equals diag 1, 2, 3 up to n. Yeah? So like if n is 4, right? Then what's D? If n is 4, then they mean, when they say D is the diagonal matrix 1, 2, 3, 4, what they really mean is, yeah, it's a 4 by 4 matrix, and everything else that I didn't write is a 0, right? So then the question about that matrix is, does D fix a basis for Rn? Interesting. Okay. And then they talk about a matrix E, which is a different 4 by 4 matrix. And then where I think you start learning some things is when you get to question 2, because question 2 says, we say a square matrix fixes a direction, although I gave that a German name for you guys, right? I said that's what you call an eigenvector, right? So if AV has the same or opposite direction, AV equals lambda V. Okay? And they ask you to explore a few things. So I think what I'd like to do here is have you guys maybe come on over to the table and work for maybe 10 to 15 minutes on this front page. And then we'll move ahead to some other examples. I think I'll give you 10 minutes. See where you guys go with the next 10 minutes on the front page. So can you give me an example of a vector that would be fixed by this?
1, 0, 0, 0.
I agree, right?
We said any scalar multiple of the identity, or E1, V.
Yes.
Vector.
Yes. I don't care what I put for that star, 0, 0, 0. This matrix will fix that vector. I agree with that. Then it says, does D fix a basis for Rn? Well, no. It's not going to fix a basis for Rn. But the reason that they're asking about this, and maybe I should do this, guys, I'm going to go ahead and ask if, so part A of question 2, I think I already explained. Explain the relationship between fixing a vector and fixing a direction, right? If that eigenvalue is 1, that's when you have a fixed vector, right? But if it's anything else, we just call that a fixed direction. Okay? And I want to, it's funny because look what part B says. Suppose that A fixes the direction of V and C is a scalar. Does A fix the direction of CV? That answer is also going to be yes, and the argument is almost exactly the same as what I did in the proof for problem 1. Part C. Does the matrix IN defined in, oh, well, we didn't do that yet, did we? Oh, we skipped it. The identity matrix, does it have any fixed directions that do not correspond to fixed vectors? Oh, all right. So the identity matrix, like if I said, maybe I'll do this one in green, I4, that would be this matrix, right? Okay. So what vectors get fixed by this thing? I don't care what you put, right? A, B, C, D. That's A, B, C, D. So the identity matrix is a really kind of bizarre matrix in that it fixes everything, right? And then question 2D is maybe the most interesting one on the page. Does the matrix D, as we wrote here, have any fixed directions that do not correspond to fixed vectors? What values of lambda occur? So what do you guys think? Maybe we didn't get that far.
We only got the F.
We only got to F. Let's look at this one though now. 1, 2, 3, 4. Give me another vector to multiply by. Something that doesn't get fixed, but might be instructive.
4, 3, 2, 1.
4, 3, 2, 1 is okay. If I do 4, 3, 2, 1, let's see what happens. Do you see what we get? What's the first coordinate going to be? 4, which I kind of knew that would happen. Because remember that anything that looks like this gets fixed. So it's almost like these other coordinates didn't get touched by the 1. Right? What happens to this one? This one's going to become a 6. The next one's going to be 3 times 2 is 6. And this one's going to be a 4. Right? So once you've done that example, then you might be able to think of, could you come up with an eigenvector for this besides 1, 0, 0, 0, for instance, or 3, 0, 0, 0. Those are all eigenvectors. But could I have another eigenvector? Something that's not fixed.
Could you do 2, 3, 3, 2?
You could. If you did 2, 3, 3, 2, the first entry would be what?
2.
2. So that part is fixed. But would the next part be fixed? No. The 3 would get sent to 6. You see that? What if I did this? And then give me a number to put here. I don't care what. 5. What does that equal? Well, right? And this gets changed to what?
10.
10. You see that? Is this vector an eigenvector of the blue matrix, D?
Yes.
Yes, it is. What's the eigenvalue? 2. Maybe this gives it away now, right? Are there other eigenvectors and eigenvalues? What are they?
The identity vector side.
Okay, so if you did this times E3, and it would get multiplied by 3, right? So these numbers here are in fact the eigenvalues, right, of matrix D. Diagonal matrix is really, actually this diagonal matrix is really interesting. The only eigenvalue of the identity matrix is 1 because anything you multiply it gets fixed, right? And what we proved, or what we could prove, I guess we didn't quite prove it, we proved that the set of all fixed vectors is a subspace of Rn. But what in fact is true is that if you give me an eigenvalue, I can find a subspace of Rn, which is called the eigenspace. It's all the vectors that would be eigenvectors associated to that eigenvalue. Okay? And so what I'd like to do now is I'd like to kind of walk you through section 1. You read it, but I feel like there's a lot in there. And I kind of want to show you some of it so that I kind of feel like working together you're going to get more out of it than just reading yourself. Okay? So I took some notes. And, you know, you guys have the definitions. So I want to go to one of the examples they have. They had an example in the book. I guess it's numbered 4.3. And so they named the matrix A. It was a 3 by 3 matrix. It was 7, 1, -2, -3, 3, 6, 2, 2, 2. At least that's what I wrote down. I hope that's right. So it says, what I'm supposed to do here is show that lambda equals 6 is an eigenvalue. And then also find the eigenspace of lambda. And this is new. I haven't said what this is yet. Eigenspace, but I'm going to demonstrate it. This is the subspace of eigenvectors corresponding to lambda. And we will, that's what we call the eigenspace. We will denote this, denoted by E lambda. Okay? And maybe before I do anything here, if I'm going to talk about an eigenspace, you might say, well, why do we start talking about a subspace when we talk about eigenvectors? And I guess here is kind of what I like to call the big computation. Here it is. To me, this kind of tells the story of eigenvalues. So, what's the only equation that you know so far in chapter 4? If you see, go ahead. Yeah, that symbol, that's the Greek letter lambda. Lambda times v. It's their lowercase l. Okay? There's a capital lambda also, but we're going to use lowercase lambda for the eigenvalues. It's funny because that letter lambda, people use it all over math for different things. Okay, but we use it, it's used for eigenvalues in linear algebra. Okay, so I want to do a little bit of work here. This computation kind of explains what's going on. So we're going to subtract lambda v from both sides. In other words, I'm setting the equation equal to what?
0.
0. First question I have. Is that 0 a scalar or a vector?
Matrix.
Let's see. We can work it out. A has what dimensions?
N by n.
N by n. V has what dimensions? N by 1 has to, right? So the whole thing together has dimensions n by 1. Now lambda is a scalar, so forget about that. V is n by 1. And so 0, when I write 0, is actually what dimensions? N by 1. So it's a column of zeros. You guys with me on that? I think that's important to understand. Okay. Any idea what I'm going to do next? I set the equation equal to 0, so I can do what?
Vector.
I'm going to factor. Now, I can't do that yet. I have to cheat a little bit first.
Multiply by identity.
Yeah, you saw that in the reading. That's awesome. So the next step is this. I'm going to write A times V is the same as, AV minus lambda IV equals 0. And this identity is also n by n. See, V is the same as IV. right? But now what you can do, and this is what was suggested here by Tyler, is since we have that lambda I, right, we can now write A minus lambda I times V is equal to 0. And that's the big identity, right? So what this says, okay, notice any eigenvector will be in the blank blank of the matrix A minus lambda I. And do you know what I'm going to put in those blanks?
Null space.
There it is. Matrix times vector is the 0 vector. That's what we called the null space. And so when I say E lambda, what you're really finding the null space of A minus lambda I. That's what you're really finding. The null space. Okay? So now, if you understand that computation, and we know how to find null spaces, so now I'm ready to do the problem example 4.3 asked me to do. So the first step, they say, show that lambda equals 6 is an eigenvalue. Well, one way you can do that, all right, is you can think about, okay, this equation. Well, let's just look at this first. A minus 6I times V equal to 0. Now, one question you might ask is, what does this matrix look like? A minus 6I. Well, I'm going to write it, and then V I'll just write as V1, V2, V3. And then 0 vector I'll just write as 0. In this case, these are 3 by 1 vectors, right? And so A minus 6I, I guess what you should notice is that where it used to say 7, what's it going to say now? 1. Because we're subtracting 6 times the identity. What else is going to change? The middle number is now a negative 3. And the bottom number is now a negative 4. Is that right?
Yeah.
2 minus 6. But everything else is the same. So basically what we have to do is we want to solve this equation. I'll just fill in those numbers for where they were. Right? That's what we're really doing, is we're solving this. And if we could solve this, then we'll get oh, by the way, doesn't this equation always have solutions? Because it's homogeneous, and so it has the trivial solution automatically. And that's the thing, guys. I don't care what you put in here, it doesn't have to be an eigenvalue. You can put any number you want, it has the trivial solution. Eigenvalues are the numbers that you put in, and this has non-trivial solutions also. It'll have a whole subspace of solutions. And so I guess the question is, how do we solve this? Well, we know, right? We're going to reduce row echelon form the matrix, right? Question to you guys. Do you want me to write the zeros, or do you want me to just do it like the book does, and we'll just know that there's zeros there? This okay? So if we reduce row echelon form this, I'm just going to tell you, to save us time, that we get 1, 1, negative 2. And maybe you can see this. Can you see that that middle row is going to zero out? if you multiply by 3 and add. And even the bottom row, if you multiply by negative 2 and add. Do you see that? That's what you get. So what does this tell me about V1, V2, and V3? Maybe another way to ask it. How many free variables do we have in this problem?
2.
We have 2 free variables. So what you might do in this problem is you might set V2 equal to S, V3 equal to T, and then what that top equation says is V1 plus S minus 2T equals 0. So V1 is equal to negative S plus 2T, right? And so maybe what I could say is the solution that I get is that V1, V2, V3 looks like what? It looks like this. It looks like negative S plus 2T S T. Are you with me so far? Now I want to rewrite it again. I'm going to say what it really looks like is S times some vector plus T times some vector. Do you see what the vectors would be?
First one would be, the bottom would be 0.
Yeah.
Middle would be 1.
Yep.
And then negative 1 on top.
Yep. And then this vector would be
2.
2, 0, and 1, for instance. Does that make sense? Okay. So what we just showed, okay, is this. We showed that a basis for, and again, I'm going to write E6, but what this means, this is shorthand for the eigenspace corresponding to the eigenvalue 6 is given by negative 1, 1, 0, comma, 2, 0, 1. So that's kind of interesting, I think. What dimension is this subspace, this eigenspace? The word dimension, what does that mean again?
2.
It's two-dimensional. It's the size of the basis, right? But if you think about what this means, okay, remember the picture is this. A is a map from R3 to R3, right? Most points get moved around. Well, one point that never gets moved around for a linear transformation, of course, is 0, 0, 0, right? We know that. But actually, in this case, there's a lot of points that what happens to them is they just get multiplied by 6. They'll be pointing in the same direction. A lot of vectors will. Like what? Like negative 1, 1, 0. If you multiply A times negative 1, 1, 0, you get negative 6, 6, 0. You could check that. Does that make sense? And negative 1, 1, 0, where is that? Well, the x direction, negative 1, would be back here in like 1. And in the y direction, 1 would be in this direction. So that's saying that somehow this vector, negative 1, 1, 0, if you apply a to it, it's going to point the same way and just be multiplied by 6. Okay? Same thing with 2, 0, 1. 2, 0, 1 would be like 2 in the x direction and up 1. So like that. Now those two pink vectors, it's hard for me to draw, but would you agree that two vectors define a plane? And so those vectors get stretched out, basically. And so in R3, there's some, it's hard for me to draw, but there's some plane of vectors that gets fixed. That's called the eigenspace. That make sense? Okay. So what you're sitting looking at here, I guess, is a lot of work associated to one example. But I thought if I go through that slowly, I thought that'd be useful. One more thing about this. We were lucky because they told me something at the start. They didn't say, find the eigenvalues and eigenvectors. They said, show that lambda equals 6 is an eigenvalue. Now, how do you know that? Well, that's the real trick. In some ways, the whole trick is, can you find the eigenvalues? Then we can find the eigenvectors that correspond to them. Okay? And so some of my research has been, how do you find eigenvalues? Although I'll show you there's a simple equation. There's a very simple equation to find the eigenvalues. Let's show it now. Let me zoom in on the big computation, right? You see this? Notice any eigenvector will be in the null space. And the null space will be non-trivial, right? Well, it turns out that A minus lambda I, okay, A minus lambda I is not invertible. Does that make sense? How do I know that? Well, suppose, oh, you know, Mitchell?
Because AX equals 0 is non-trivial.
That was one of, you're remembering the fundamental theorem of invertible matrices. And one of the big things was, if AX equals 0 has non-trivial solutions, then you're not invertible, right? So you're right. That's the whole key. Well, it turns out that there's another way, which some of you have been talking about nonstop since we started talking about inverses. There's another way to tell if a matrix has an inverse. And it's the section that we're skipping. I guess I didn't show you the calendar. Well, no, I did, right? So for today, you guys had to read 4.1, and I said I would start talking about determinants, right? But I said don't read it, because I looked at it's a long section, and I said, well, we'll read that over spring break, okay? We'll come back and take a quiz on that after spring break, that Tuesday. I want to talk more about eigenvalues and eigenvectors. In my mind, that's more important. You'll see why. I mean, we get a nice equation with determinants. The equation we get, okay, since I know that this is not invertible, I get the equation determinant of A minus lambda I. Do you know what it has to equal? 0. If the determinant is 0, that means the matrix is not invertible. So, basically, again, the question is this. How do I find eigenvalues? Right? Well, one thing we can say is that the eigenvalues are solutions to the, and this has a name, so I may as well write it down, It's called the characteristic equation. Okay, and the characteristic equation is determinant of A minus lambda I equals 0. And I noticed that you had a nice example. Yeah, it was example 4.5 did a pretty nice job of this. Maybe we should go through that. So in the example 4.5, I don't have the matrix. Let me open the book and see what it was. So the matrix that they did, A was 3, 1, 1, 3. That's a nice example. Okay? So if we wanted to talk about A minus lambda I, that would be this matrix. 3 minus lambda, 1, 1, 3 minus lambda. Does that make sense? Now the question is, do we know how to find the determinant of a matrix? Well, for 2 by 2 I do. The determinant of A minus lambda I would be 3 minus lambda times 3 minus lambda, right? And then what?
Minus 1.
Yeah, because it's minus 1 times 1. So it's, 3 minus lambda squared minus 1. And I guess if I work that out and put it in order, I get lambda squared minus 6 lambda. Then I get plus 9 minus 1, so I get plus 8. Right? So this is called, by the way, this has a name also. This is called the characteristic polynomial. That polynomial. If it's a 2 by 2 matrix, your characteristic polynomial is degree 2. We just use lambdas instead of x's usually. And can you solve, oh yeah, so the characteristic equation is take that polynomial, set it equal to 0. And do we know how to solve that equation? Well, the answer is, for 2 by 2, yes. How do you solve it?
Factor.
If you're lucky, you factor. Quadratic
Equation.
formula, right? How many, you guys are all familiar with that, right? Okay, so we have the quadratic formula. Yes? No? Okay. Negative b plus or minus square root of b squared minus 4ac all over 2a. Or, does it factor? Are we really lucky here? I think they were nice to me, right? Lambda minus 2 and lambda, there we go, lambda minus 4. So what are the eigenvalues?
4 and 2.
Yeah, 2 and 4. These are the eigenvalues. Okay? Now, is this a good way to do it? Well, I don't know. What if you have a 3 by 3 matrix? Do you know how to find the determinant of a 3 by 3 matrix? Well, you will by the time I leave today. That's one of my goals. But even if you do, then you get what size equation? It would be cubic. Do you guys know how to solve a cubic equation? Yeah, kind of?
Yeah.
Is there a cubic formula? Well, the answer is there is, and it has a great history. And the first time that complex numbers were ever used, or imaginary numbers, was when the cubic formula was invented. Great story. You guys know the complex numbers? Yeah? All right, so we'll talk about that maybe in a little bit.
Dr. Stitz told me that story.
Oh, it's a great story. And then I just told it to my algebra class last time I met them, last Thursday. But then, what if you have a bigger equation? So this is something I did not tell my intermediate algebra class, okay? And this is a really cool, this blew people away. So people have known about the quadratic formula for thousands of years, maybe 2,000 years, more than that. People knew about the cubic formula that was developed in the 1600s, maybe, somewhere in that range. And there's a quartic formula. But then, in the late 1800s, a mathematician named Abel used algebra, I'll say abstract algebra, to prove that there is no formula to solve equations of degree greater than or equal to 5. This blew people away. The mathematical community was stunned. But he showed it's impossible to come up with something like the quadratic formula for anything higher than degree 5. And how he did it, I remember my graduate abstract algebra course, we spent basically half of the semester deriving that result. Okay? We worked our way there. By the way, this guy was very young. I think he was 19 years old when he proved this. And he died, I want to say he might have been about 23. He died in a duel over a girl. That's another good story, I guess. Or bad story, I don't know. But he developed some amazing mathematics at a very young age. And what does this mean to us? This means that, at least in my mind, I don't want to spend enormous amounts of time on determinants. Because even if I come up with the equation, in general, I'm not going to, just like I'm not usually going to be able to factor, I'm not usually going to be able to solve it exactly. Well, what I can do is I can solve it iteratively. You guys in Calc 1 studied something called Newton's method. Or even in this class, we did the Gauss-Seidel stuff. So you can approximate eigenvalues. And that's more what's done.
So if it has, for like a 5 by 5 or greater, you have to approximate it? I mean...
Probably.
6 by 6.
Yeah, even 5 by 5. Greater than or equal to.
Oh, yeah.
I mean, unless somebody made up a really nice example, like this one. This is a symmetric matrix, so I know some things about it, which you guys will learn shortly. You're going to learn a lot, okay? But you're right. We can't expect we're going to come up with the exact values of these eigenvalues. And so in this chapter, you're going to learn a lot of things that I certainly didn't when I studied eigenvalues. Yeah, but I said I would try and have you guys walk out of here with a knowledge of how to do determinants. So maybe we'll do that. Ready? So, should we find the determinant of my favorite matrix? That's a good idea. Let's find the determinant of 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So I guess, these were the notes for 4.1. And now I'm in section 4.2. And I will have a lot more notes after spring break for you about determinants the day we come back. But I don't want to do much until then. I just want to show you kind of, the basics. And some people would say this is really all you need to know is what's the formula? How do I compute this determinant? Okay? And there's a theorem in your book which is really nice to have. Yeah, so here's my notes on it. Oh, yes. Have you guys heard this name yet? Laplace? Yeah, it's a shopping center by Beechwood Place, but it's also a mathematician who, his name's going to come up again in your courses, okay? The Laplace expansion theorem, this is what we're actually using to compute the determinant. And it says we can use any row or any column to do it. All right? So what do you want me to use, a row or a column?
Row.
Okay, row what?
1.
Row 1. All right? Tell you what, I'll use row 2, and then I'll have you guys do it with row 1. All right? We'll see if we get the same thing. Laplace says we're going to. One thing you have to do, okay, and what I'm about to do is what's called expansion by cofactors. You need to use the checkerboard pattern. Plus, minus, plus, minus, plus, minus, okay? So what happens here is I look at that matrix, and that tells me that as I go across row 2, what are the signs I'm going to need? I'm going to need minus, plus, minus. Okay? So I'm going to say the determinant equals minus a determinant of a smaller matrix plus a determinant of a smaller matrix and minus a determinant of a smaller matrix. Okay? This one might be called, this little matrix here might be called A row 2 column 1, A row 2 column 2, A row 2 column 3. And these things here, it's called the adjoint, Aij. What you do is you delete a row and a column. All right? So watch how this works. Oh, see how that's a 4, guys? I should have minus 4 times the determinant of the matrix I would get if I deleted that column and that row. And that would be 2, 3, 8, 9. Do you see that or no? If I deleted the column that 4 is in and the row that's 4 is in, I would be left with 2, 3, 8, and 9. Then we're going to have plus 5 times the determinant of, do you know what matrix I'm going to write? 1, 3, 7, 9. That's right. And then we're going to have minus 6 times the determinant of what matrix? Well, there's 6, right? So delete that column and that, or that row and that column. What's left? One and 2 are left, and what else?
7, 8.
7, 8. Mitchell, you with me?
Yeah.
Yeah? Okay. So it's interesting. To do a 3 by 3 matrix, you have to know how to do 2 by 2 matrices. To do a 4 by 4 matrix, you go across any row or any column and do a bunch of 3 by 3. So this is what you call a recursive definition, which means if I have a 1000 by 1000 matrix, even with a computer, computing the determinant is extremely tough to do. And chemistry people may have million by million. Or the Google matrix is billions by billions. And you can see that this is not the way to do it computationally. But from a theory standpoint, it's important to understand that this is the way to do a determinant. Okay? And so it's good to practice this at least once in your life. So let's see what I get. I get negative 4 times what? I guess this would be 18 minus 24 plus 5 times the quantity 9 minus 21 minus 6 times the quantity 8 minus 14. Okay, so I get negative 4 times negative 6 plus 5 times, is that negative 12, right? And then I get minus, this is 6 times negative 6. So I'm getting, let's see, that's 36, and that's 24, that's 60, minus 60 from the middle term. Sure enough, I get 0. And what does that tell me?
It's not inverted.
Yeah, my favorite matrix doesn't have an inverse. I love that matrix. And again, what the Laplace expansion theorem says is if you did it using a different column or a different row and you followed the checkerboard pattern for the signs and you put in the coefficients and the correct matrices, you would get 0. Any questions? Yes.
So if you had a matrix that was like a 5 by 5, you have to keep doing it
Yes.
for each smaller matrix.
And I can still remember being in college. And this was, we did it in Calc 3 because they decided, hey, this is a good idea for people to know. So even though it's calculus, my first test was all on matrices. And I learned how to do determinants. And the test had 5 by 5 matrices on it. But fortunately, the 5 by 5 matrices had lots of zeros all over the place. So if you were smart, you picked a row that had lots of zeros and maybe one non-zero entry. You see what I'm saying? Actually, even the one we had earlier today. Here. Yeah, matrix D. Remember this one? What would be the determinant of this matrix? Let's find the determinant of D. Well, let me expand across this row. Okay, so it's 1 times the determinant of the matrix that has the diagonal 2, 3, 4. What? Well, it's interesting because now I'm finding the determinant of this 3 by 3, and I don't need the negative anymore because now it's here in the upper left-hand corner. The upper left-hand corner is always positive. So I'll expand across this row again. So it's 1 times 2 times the determinant of this matrix. Oh. So what's the determinant? 1 times 2 times 3 times 4, right? Do you see it? 24. I don't care that it's 24. What I guess I do care is, what's the determinant of a diagonal matrix?
Non-zero.
Yeah, it's just the product of the diagonals, right? And actually, if you think about it, we go back to this equation, right? Let's do that problem over again. Suppose I said, oh, we're having trouble seeing now because this came out, huh? Let me pause it and reset it. If I told you guys, find the eigenvalues of matrix D, right? One way to do it would be determinant of D minus lambda I is equal to 0. Well, when you subtract lambda I, you just get 1 minus lambda times 2 minus lambda times 3 minus lambda times 4 minus lambda equals 0, right? So I guess here's an equation I can solve this degree for because it's already factored. So diagonal matrices are really nice. And actually, it may not surprise you that even if I had non-zero stuff up here, right, this would still work. The determinant would be this. And that means any upper triangular matrix, you know what the eigenvalues are just by looking along the diagonal. So that's another nice little fact. And there's plenty of more. We'll do a lot more Well, next class.